So continuing with the list of conjectures here, let me show you the computer that was used to show that 2 to the 2 to the 2 to the 2 to the plus 1 is not always a prime. This is the so-called SWAC, or the Standard Western Automated Computer. It was built around 1950, and this experiment that I just performed in Maple for you is as by many people seen as the beginning of experimental mathematics. So I looked up the date. It is August. Where did it go? August 14, 1953. So this is when this experiment was made. The SWAC was situated at the United States National Bureau of Standards, and Selfridge, who did this experiment, is an eminent number theorist who did this in his young days. I've been sort of wondering why this took place at the National Bureau of Standards, because this is not an academic institution. Actually, I think I have the explanation. Um, so Lemur, who I mentioned earlier, who was also a number theorist, a very prominent one, was a professor at the University of California in Berkeley. And at the time of the McCarthyism, you had to sign an oath or give an oath that you weren't a communist, essentially, around 1950. And he refused to do this along with some other people and was consequently fired from his position. And then he started working at the National Bureau of Standards. Then there was actually it went to the Supreme Court, and it turns out that this was an illegal oath, so he was reinstated in his position. But those years when he was working at the National Bureau of Standards, he was actually sneaking in a little bit of mathematics while doing his day job. So that's why the SWAC was one of the most important early computers in number theory. And then actually, when he was reinstated, he managed to take it with him. So the computer was used by the University of California for quite some time. Now, I don't know so much about how this old computer works, but I do know the specifications of the program of the computer when it comes to memory. It had 1.2 kilobytes of RAM, and so you saw me do this experiment that very almost instantaneously let my computer reserve 36 megabytes of RAM just to represent the number. So you have to wonder how this was done. And in fact, maybe that's not so surprising as you might think, because the number that we're looking at, if you write it in binary, if it's of course it's 2 to the something plus 1, so it's like a 0 and then a bunch of so it's a 1, then a bunch of zeros, and then a 1. And if you divide that by a number which also has a very specialized form with lots of zeros and a 1 at the end, then you don't have to save all these zeros, right? So you can, if you're clever, you can do it much less space. And the point that I'm trying to make is that you had to be clever in order to do these things at the time. Things that you can instantaneously now do on a standard computer with something like Maple. Okay, so this was the first example by Selfridge. Let's go on to the Goldbach conjectures. So let's talk about the second Goldbach conjecture, the other Goldbach conjecture first, the one that says that every prime is the sum of, every odd number is the sum of a prime and twice a square. And actually, so let's do this in Maple. It's very easy to write a little program that checks these kinds of things. So I wrote a program called sum of prime and twice a square. The way it works is that you take n as your input, and then you're wondering if n is the sum of a prime and a twice a square. And the way I did this is I just went through all the possibilities for twice the square. And there aren't that many possibilities for twice the square because, of course, 2 times I to the I squared has to be less than n. So that means that the number that I'm squaring has to be less than or equal to the square root of half of n divided by 2. So that's what I'm doing here. I'm saying, okay, let's go through all the possible i's from 0 to rounded down the square root of n over 2. And then I'm just asking Maple, when you subtract 2 times I squared, you get a prime out. And if you get a prime out, then you're done. You've proved that this satisfies Goldbach's conjecture. And if not, you keep going. And if you make it to the end, you have found a counterexample to Goldbach's conjecture. So going through this from all the odd numbers from 3 to 10,001, you get the two counterexamples that were actually found by Stern, German mathematician. So you can see that this takes not very long time, and of course this would easily have been doable at the time of Goldbach. You could simply sit down and do this systematically, but you know, the people who I mean, nobody seemed to do this until Stern came around. So this was resolved pre-computer, and you can see that doing it in something like Maple is very fast. What's interesting here is that actually, if you were to change this number into something much bigger, you wouldn't find more examples. As far as I know, there are no other counterexamples known than the ones that we have on the screen already. So of course you might make another conjecture saying that these are the only ones. You can also change the rules slightly and say that it has to be a non-trivial sum of twice the square and a prime. So what I mean by that is that if you have a prime number, then that is not automatically qualified because p is the same as p plus 0 squared. I want a non-trivial 2 times 0 squared, I should say. I want a non-trivial double square. So I can just change the program so that I start with I equals 1. And then when I do that, I get some more numbers out, some new numbers that are primes, but not of the form prime plus 2 times the square non-trivially. And this is there's a business around us, an industry around this called Stern primes, which is a very interesting problem that sort of comes out of these kinds of computations. So this is an example where the counterexamples were not very far away from Goldbach. When you talk about the other Goldbach conjecture, the one that says that every even number is the sum of two squares, then that turns out to be a long story. But I just want to point out that it's pretty easy to check these this conjecture on many primes by being slightly clever about how you test this. Because of course you could do something like what I did in my program. You say, okay, I want to test that every even number is the sum of two primes. Then I could say, okay, here's my even number. Now I go through all the primes up to half that even number and subtract that, and then I see if what I get out is a prime. I mean, that's an algorithm that would work, but you have to be, in order to check this, up until 10 to the 18 certainly, but also, you know, even much smaller, you have to be slightly more clever. And there's a fairly easy way of doing this that is reminiscent of the Siever-Verhulst nest for finding primes. So let me explain how that would go. So 4, of course, is the sum of two primes, 2 plus 2. But there's something very special about this because all those numbers are even. So for all the other even numbers, if you want to write them as a sum of two primes, those two primes have to be odd. So in order to not have to deal with the prime 2, which is sort of an odd prime, you want to do this separately. So I will start by saying, okay, 4 is not a counterexample, and I'm not going to deal with the prime 2. Now I go through the numbers and I look at the number 3, and I say, okay, 3 is a prime. And that tells me that 9 is not a prime, and it tells me that 15 is not a prime because this is 3 times 3 and 5 times 3 and so on. So I could put I could strike out these numbers, these odd numbers. They are not primes. Every 6 entries, I will note that this cannot be a prime. I can also see that 6 is not a counterexample to Goldbach's conjecture because 6 is a sum of 3 and 3. And then you sort of keep going this way. You move on to 5. 5 is a prime because we haven't stricken it out yet. Numbers like 15 and 25 and so on, these are also not primes. And furthermore, we can see that 8 and 10 are not counterexamples to Goldbach's conjecture because I can take 5 and I can add 5 to it, I get 10. I can take 5, I add 3 to it, I get 8. And so those are not counterexamples. I move on to 7. That tells me that 14 is not a counterexample, and so on. And so you can see I here, this is a way of making an algorithm which is efficient because in time, because I spent some memory on keeping track of the status of the various numbers. And so by doing something like this, you can actually check the Goldbach conjecture very far. This has been done up to, as I said, something like 10 to the 18. And of course, that doesn't really solve the Goldbach conjecture. It just tells you that if there's any counterexamples, then it has to be big numbers. But somewhat surprisingly, these computations helped in establishing what's called the ternary Goldbach conjecture, which is this sort of same idea. This time we say we look at an odd number and we allow the sum of 3 primes. So Goldbach, I think he also conjectured this himself, but I'm not 100% sure. But the question is, can you write every odd number bigger than 7 as a sum of 3 primes? And this is now actually something we know as a mathematical fact, because Helfgott was able to prove that every odd number, very big odd number like 10 to the 30, is the sum of 3 primes. And then he could use essentially the information that we've seen from the partial verification of the good old Goldbach conjecture to show that the numbers up to 10 to the 30 is the sum of 3 primes. So we'll return to how this is done. Also, when you try to do something like this, you run into a slight issue that has to do with the way something like isPrime works. So isPrime in Maple is actually not something that you should trust 100% because this is an example of an algorithm that works via some sort of pseudo-randomness. And so it tells you actually that a number is a prime or isn't a prime, not with mathematical certainty, but with a very high probability. So when you deal with these kinds of things, you have to be careful. And so this is something that we need to return to.